Testing, there we go. On this problem, we have negatives, we have things being stretched, we have things moving up, down, left, right. When you're on the SAT test and you have a question like this, it's smart if you can throw out some that you know can't be right. Who wants to nominate one of these you know can't be right? It looks really messed up compared to what it should be. What do you think? All right, why do you want to throw out C? So the vertical stretch number is goofed up. It's supposed to be a stretch of 4, and this one says 3. You're right. We throw it out. Now we have a 1 in 3 chance of getting this one right. See, what you want to do is increase your chances down to hopefully 50-50. If you can get it down to 2 things and you're not sure which it is, at least you have a 50-50 chance. It really makes a difference. Okay, who wants to nominate another one that cannot be right? A, because why? It's all, tell me if I think I'm right that it's all on the inside here. There's nothing on the outside. Well, there is a negative, but there's supposed to be a stretch factor of 4 on the outside, and this isn't on the outside. So you're right, that's out. It's also just kind of goofed up on the inside too. The 3 and the 9 were all messed up. That leaves us B or D. I'd like you to make a guess on the Centio unit that you have in front of you. Hit enter. And I think this little green dot that you can't see on the recording, but it's off to the side here, is telling me everybody's answered. All right, so I hit stop. And almost everybody said B, and some of you said D. All right. Usually in a situation like this, then the people that said B, as in boy, are right. Unfortunately, this is not one of those times. Who said D? Because you're right. Nice job, D, people. Now, why is B wrong? Well, it actually looks almost identical. What's the only difference between B and D? For a set of parentheses. So hopefully this is telling you that those in parentheses are important. Because if you don't have the parentheses in there, it'll be wrong. This one is wrong. This one is right. Now this one, I know you're thinking, well, doesn't it move to the right 9? No, it actually doesn't. Because when you factor this 3 out, you'd have x minus 3 in there. If you actually graph this on a calculator, it will only be moved over to the right 3 places, not 9 like it looks like it is. Okay? This one would actually be moved over 9 places. All right, so those parentheses are important. I knew I'd catch a few people doing that. All right, moving on. Now we're doing some transforming. This was transforming from a normal parabola, which just looks like this, and we're stretching it and moving it and all kinds of complicated stuff. I had a little clip from Transformers that I wanted to show you. So I'll hit pause. So back to, here is a typical domain question. Would you please write this one down? Now you may remember from Friday, we were talking about solving these things. In fact, we were talking about it on Thursday and a little bit on Wednesday too. So this has been a big focus, is getting domains figured out. These domains are what numbers would work versus what would not work. And specifically the domain, you're supposed to list all the numbers that would work. So what you don't want to try to figure that out. You really want to figure out what are the numbers that won't work. So this part right here, I set greater than or equal to what? 0. So x has got to be greater than or equal to 0. And this part right here, I set what? Not equal 0. X minus 2 cannot equal 0. They're different. On the top one, it can be 0, because square roots, it's okay if they're 0. They just can't be negative. On the bottom here, it can't be 0. It can be negative, but it can't be 0. So those are different things. This one boils down to x is greater than or equal to 0. This one boils down to x is not equal to 2. And so those are my 2 points, 0 and 2. And I strongly recommend a number line. Here's 0, here's 2. And I ask myself on each spot, will it work or not? Will it work at 2? If I put a 2 in there, do you see a problem? 2 does not work. Will it work at 0? Yes, because if I stick in a 0 here and here, I don't care if the denominator is negative, and I don't care if a square root of 0 happens. That's okay. So this one works. Now you have to ask yourself, where is it going to work? Now I know some of you are just thinking, oh, it just has to be all positive numbers, so all of these work all from there over. And that's not right. Don't just look at one thing at a time. If I were you, I would check each little interval. I would check -1 here. I would check 1 there, and I would check 3 there. Would you please do that right now? And figure out where it actually works, and then write me the interval answer for that. All right, testing. Testing, testing, 1, 2, 3. Testing the 1. I put a 1 there and there. Do you see any problems? Nope, it works. I test a 3. I put a 3 there, I put a 3 there. Is there any problem with a square root of 3 or a 3 minus 2? No, those are okay. I test -1. I stick a -1 right in here, and I instantly realize, oh, I can't do that. I can't have a negative under the square root. So it doesn't work. All right, so my final answer is between 0 and 2, and 2 to infinity. But I got to write it right. 0 to 2 with bracket, parenthesis, union 2, parenthesis, to infinity, parenthesis. Raise your hand if you had that one right. Okay, good. That's your basic domain kind of thing. All right, moving on. What we need to learn about now is local minimums and maximums, and then intervals that are increasing or decreasing. And then we got to learn some stuff about the degree of a function. All right, let's start out with the minimums and maxes. Just sketch this little thing right here. Just a quick sketch of a wavy graph on your paper with your pencil. The high spots, those are called local maximums. The low spots, like here and here and here, those are called local minimums. Now let's make sure you understand the difference between a local maximum and an absolute maximum. Maximums are these red spots here, the high spots. And let's think of that as high IQ, okay? They do an IQ test on kids sometimes when they're younger. Some of you probably never had an IQ test. Others of you probably have. Let's say that they test your IQ. IQ usually averages around 100. Okay, most of you guys are probably in that 100 to a little higher zone because we are in an accelerated class here. All right, now if your IQ, let's say you have the highest IQ in the class, and let's say that that's 128. Okay, let's say you have the highest IQ in this class. Are you the local maximum for this class? Yes. Are you the smartest kid in the entire world? Probably. No. That kid would be the absolute maximum. Okay? Let's say that it's a kid in Germany, incredibly smart, 198 IQ, okay, at age 16 or whatever. So that kid with 198 IQ, is he the local maximum? Locally, isn't he the smartest kid? So you can be both. You can be the local maximum and the absolute maximum at the same time. Is every local maximum the absolute maximum? No. Only one of them can be the absolute maximum. But can be a lot of local maximums. Okay, there's a lot of local smartest kids in the school. I'm not going to name names, but you probably have seen some kids from our school that are pretty smart. Some of them gotten into Harvard or etc. Some of our seniors last year. Pretty smart kids. Okay, and locally, they are our local maximums, so to speak. And when they go off to Harvard or whatever, then they're in there with a whole bunch of other really smart people, and they probably aren't the local maximum anymore. Know what I mean? Because there probably is some other kid there who's really, 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 really smart. Okay, and then that kid is not only a local maximum, he's the absolute maximum at his college. Okay, anyway, so if we were talking about this graph, here's the thing that always throws kids off. They'll be like, okay, this spot here, It's not a local minimum because it's the absolute minimum. That's wrong, because that spot is really what? It's both. It's both a local minimum and it's the absolute minimum. This spot here, another common mistake. Okay, it is a local maximum, and they're right about that, but then they'll say it's the absolute maximum because it looked higher to them than the other point. But here's the thing they're missing. Do you get that it's higher over here? Even that it isn't a little peak, it's still going up. So the function hasn't even reached its highest point. In fact, will it even ever stop? No. So therefore, this has local maximums. The local maximums would be here and here. But it does not have an absolute maximum because there is no max to this graph. It goes up forever. All right, so I'm going to give you a couple quick shots on that. This graph, does it have a local minimum? Stare at it. Is that where you're staring? Good. Does it have a local maximum? Is that the absolute maximum? No. Because why? Because it goes on forever and there is no max. How about the absolute minimum? Does this have what an absolute minimum? No. All right, this graph right here. Does it have an absolute maximum? There it is. What about that guy then? Local maximum. Technically, this is two things. Local max and absolute max. Yes. Yep, we have to assume from what we see that the graph is not going to come back up and go higher. I know what you're saying. But we have to assume that if it did, that the person making the problem would have to show us that. With this, though, heading down, we can assume that it's going to keep going down forever, and therefore there's no absolute minimum. There's a local minimum right there. Yes? Yep. Yep. Although unlimited is a big word. Yeah, see, if it's sine, graph of sine goes like this, goes back and forth, then it has no limit to how many local maxes there are. Yep. All of these would be local maxes. All these would be local minimums. And there isn't, on sine, it never goes any higher than 1. It's the highest it ever goes, and so therefore it has a maximum. And any one of these is not only the local maximum, it's the absolute maximum. It's kind of a weird one because it has lots of them that are exactly the same height. All right, so what have I been teaching you so far? So far, you've hopefully figured out what local minimums and maxes are about. Okay, now we got to talk about intervals where the graph is increasing or decreasing, and this is the simplest part. Do you get that this is a spot where the graph is increasing, right, from down here up to there? Is that the only spot on the whole graph where it's increasing? No, there's multiple spots like that. How would I describe this spot? I'd say it is from 2 to about 3.5. So I'd write from 2 to 3.5 is where it is a spot where it's increasing. Now there's argument about whether these should be brackets or parentheses. The fine point argument is this. At the moment that it hits 3.5, is it still increasing at that moment? No, because after that, it's going to start going down. So to me, it seems like these should be parentheses. But in some of the math books, they say like this. So bottom line is, don't worry about whether it should be brackets or parentheses because there's a good argument for both. I think parentheses make more sense, but I'm not going to mark you wrong because if your book does it that way, I can't really argue. Okay? So for your increasing and decreasing intervals, it's okay to use parentheses or brackets, but I think parentheses make more sense. Where is it decreasing? Well, here's a spot. It's decreasing from about half to about 2. So 0.5 to 2 is a spot where it's decreasing. And I'd use parentheses. You could use brackets, it'd be fine. Okay, so that's how you say increasing and decreasing intervals. Super simple. The next part is more a review of something, the lead coefficient and the degree and stuff. Those are things that you learned in higher algebra. Do you remember when you had a graph like this that you could say it was third degree because it has 3 cut throughs that are all worth 1? Is this ringing some bells? Okay, how about this one? This is degree 2 because it bounces. Do you remember when the roots are a bounce like that? It's worth 2. All right, so what do you think this guy's degree is if it does that? Yep, degree 3. 2 for this one, 1 for that one. So that's degree 2, that's degree 1, total degree 3. This is a third degree polynomial. Get that? Okay. True or false? This is a 4th degree polynomial. True. It's got a bounce and 2 cut throughs. Next question. This has 2 local maximums. True or false? True. It has a absolute maximum. True or false? True. It has a local minimum. True. All right. Now, one more thing. Do you remember that a parabola that looks like this compared to a parabola that looks like this, the only difference is that the one has been flipped, right? And the only difference then is that this guy's equation is y equals negative x squared. A negative on the outside makes it flip, right? Well, that's the way we used to think of it. But now you need to think of it this way, that any function that ends up at the end going up like this, I know that that function has a lead coefficient, the number in the front of it has to be positive. This has to be a positive. It can't be a negative there. If there was a negative, it would be going down at the end of the function. All right? How about this? It's a 1, 2, 3, degree 3, so it probably has to be a 3 there, right? And then this number in the front of it has to be positive because it's going up at the end. Don't think about how the other end, it doesn't even matter which way this end is going. We don't care. But if on the right-hand side it's going up, then it's positive. So on this graph, would this be an okay possibility? It's degree 1, 2, 3, 4. So it'd be x to the 4th. Is this an okay way for this answer to start? Nope. Because why? It has to be negative because it's going down at the end. So it has to be a negative in front. All right. Next, if you were going to try to figure out this one and it goes and bounces here, cuts through there, do you remember, actually let's make it cut through again down here. Do you remember that this spot here, bouncing, is worth 2, and this is worth 1, and this is worth 1, makes this a degree 4 polynomial? Yes, you get that? Okay, how about this? What if that's at touching at negative 1, this is at 10, and this is at negative 9? Do you remember that we could have an equation that would be 3 parts, one of which is for this spot right here, and that would be like x minus 10? Does that ring a bell? I know it's been a while. I'm going to pause for a second here. Thank you. So this one has an x minus 10 here, and it's a cut through. This one's a bounce at minus 1. So I'm going to put this one in right here, and that would be x plus 1, because we want that negative one to solve it. Do you remember this? Does this? I hope this works for you. And then this guy right here is at x plus 9, because we want the negative 9 to solve it. And then this one being a bounce means it's worth 2, so I put a 2 right there, where the other ones are only cut throughs, so they're worth 1. That was a long time ago, probably 6 months ago, that you learned that. I know that you talked about it. In fact, I'm pretty sure you had a quiz that was just like this at one point last year. All right, so I'm going to do one more and see if you get this. I'll make this one simpler. Say it's bouncing at 3, it's cutting through at negative 1. I want you to write me a little equation like I just did a second ago for this polynomial. Hopefully you wrote x plus 1 for this one. And hopefully you wrote x minus 3 for that one. And one more thing. Squared on this one because it's a bounce. There's the equation for the graph I just made. Now, yes, you can make it more complicated by having a stretch factor out in front, like this whole thing be stretched like a 5 or whatever. You could put that in there. And the only other thing you should watch out for, and kids always forget this, is that on a graph like this, if it's going up at the end, what does that tell us again? Positive in the front of it. Okay, so this number would have to be positive. But what they'll do is they'll have a graph just like this that ends going down, and they forget to put the negative in. Now, this does not need a negative up here. But if the graph had been going down at the end, you'd have to watch out and throw a negative at the front of it. Okay, so tell me about this one. Degree what polynomial? Degree 4. Okay. What's that spot called? A bounce. These are two whats? Cut throughs. And does it have an absolute maximum? Yep, right there. Does it have an absolute minimum? No, because it goes down forever. Does it have a local minimum? Yep, right there. Does this thing, the fact that it's going down at the end, does that tell you something? The lead number is what? Negative. If I was going to write an equation for it, and this is at 3, and this is at 7, and this is at negative 3, then I would write this. Y equals 3 sets of parentheses. And I'd make one for this, which would be x plus 3. One for this, x minus 3. And one for that, x minus 7. It's supposed to be an x. And then only one of them would have something special, and that would be the bounce. Squared right there. 4th degree polynomial. All right, so there's a quick reminder about all that polynomial stuff. Okay. Last thing I need to make sure is that you know how to find an absolute or local maximum and minimum on a calculator. Do you see this blue picture? Do you see how that's a local maximum? To find that on the calculator, there is a thing under second calculate where you can calculate a maximum. You know how on those other ones you'd go just to the left of it and you'd hit enter, and then you move the little spider over to the right of it and then hit enter, and then hit enter right at the spot? You do the same exact thing, except you look for a maximum. So grab your calculator, type this in. You want x minus 2 and an x plus 3 in parentheses squared. Okay? Just like you're seeing on the board there. Type that in. And I'll show you how to calculate the maximum or the minimum. Once you got that typed in, hit graph. Here, let me just move this over here so I can have my calculator up at the same time. There. And I hit graph. And my graph looks pretty nice because I Z-boxed it. I zoom with a box around the area that I wanted to zoom in on. And I can see it really well. And so then I go second, calculate. And I want the minimum or the maximum. Well, I started out talking about maximum, so let's do that. Let's do the 4. Left boundary, that means go just to the left of it. There's my little spider just to the left of it. I hit enter. And then go just to the right of it. And hit enter. And then go right on top of it and hit enter. And it says an answer that at first makes sense. Negative 2.99999, that's about negative 3. And that makes sense to me. And then it says this other weird number. The y is negative 7.05 e negative 12. What in the heck is that? That's your calculator's way of saying it's really, really, really close to what? 0. Now think about it. The height of this, isn't that almost touching the line? Well, it looks like it is touching the line. It looks like its height is 0. So why doesn't it just say 0? Well, it has this, which is really close to 0. It means take the decimal in 7.05 and move it 12 spots to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Do you get how 0.0000000000705 is really close to 0? That's what it's trying to say. Now, the weird thing is, why didn't it just say 0? I don't know. And if you try it again with your same calculator, look at the number you have in your calculator. I bet yours is different than mine, first of all. His is like negative 5.7 times 10 to the negative 12. hers over here is negative 5.8 times 10 to the negative 12. Yours didn't get it yet. Kind of sad. All right. This one is negative 5.75 times 10 to the negative 12. Okay, so the point is, this is a number that is an approximation. And so therefore, you just need to know that that effectively means 0. So its height is 0. Okay. Now, I'd like all of you, including the people that didn't have a calculator before, which there's ones up here for that purpose. Please take one. Okay. Anybody else that doesn't have one? Hurry up. I want you to try the other one and do the minimum. Find the minimum point for this part of the graph right here. It's the same exact process. Second, calculate minimum. So you're typing in this equation right here, and then graphing it, and then going second, calculate minimum. Calculate minimum is the 3. Now we got to go over to this, be just to the left of it. Uh-oh, a little farther than I wanted. There we go. Left of it, right of it, right on top of it. That one's a little more normal. 0.33333, isn't that the same as pretty much 1/3? And then the y of it, which is the actual height of it, which is what we want when you're doing minimums. You want to know how high or how low was it, is negative 18.5. Raise your hand if you got that correct on yours. Okay, good. All right. Any questions? You should be able to, if I give you a graph, you should be able to find its absolute minimum really, or local minimums, really easy by using that. I know you'll have to do that on the test or something like it. That's why I wanted to make sure you could do it by hand on the calculator. Okay? I mean, with your calculator. All right. So I'm going to just make sure that I don't have anything else. That stuff is for tomorrow, so we don't have to worry about that. All right, good.